No problem. So I'm Alessandro, and I'm going to, so this is work with Anthony Kennedy and Mark Giolami, who is my supervisor, and I'm going to talk about basically the application of Hamiltonian Monte Carlo to sampling. So I'm gonna talk about a bit the background, some background on HMC, Hamiltonian Monte Carlo, just because I'm not sure how many of you are familiar. And then I'm going to go on to the application of HMC on Lie groups and homogeneous manifolds. Yeah, so the goal of HMC is to sample some target distribution P over a manifold M. So sampling means we're going to basically approximate P by defining some chain Xi and replacing P by an empirical measure. For HMC, we need to assume that P has a density of the form E2 minus V with respect to a reference measure that I call vol here, which is usually the Riemannian volume form. So you're going to have a Riemannian metric on M, except on Hilbert space HMC, in which it's the Gaussian measure, and on statistical manifold HMC, in which it's going to be just the Haar measure, so just a Lebesgue measure, while your metric is going to be essentially your Fisher metric. And you only need to know your density up to normalization, which is very important for application to Bayesian statistics or molecular dynamics, in which your normalization is the partition function, which is very expensive to calculate. And so another reason why you want to do that is because once you have some samples, you can approximate the average over any observable f with that estimator, which is basically just the integral of f over the empirical measure. So we've seen many examples of manifolds which arise a lot in application, and some of the measures would be, for example, some of the applications include like the Fisher-Bingham family of distributional Stifel manifolds. You have, so those are particular directional statistics. In molecular dynamics, you have the partition function, in which the manifold of interest is defined by holonomic constraints, because basically you're going to fix some of the degree of freedoms, the bond angle, the bond length of the flexible manifold. That's going to define some holonomic constraints. And so you end up having to sample that distribution over the holonomic manifold. And so recently there's been also application to the Grassmannian manifold or space of positive definite for learning the spectral density matrix by Andrew Holbrook. So in HMC, remember your density is E to the minus V, and you view V as your potential. So V is the minus log of the target density. And what you do, so your distribution is on the manifold M, but what you're going to do is that you're going to lift your distribution to a fiber symplectic manifold, which can be Tm or T star M. So Tm when you have a Riemannian metric. And essentially that's going to introduce a Hamiltonian once you fixed some horizontal distribution, some vertical distribution over momentum. And that's going to introduce a kinetic energy, T. And the point is that Hamilton's equation, which you can see there, the point is that those preserve both the symplectic volume, so Wn, and the Hamiltonian H. So they preserve the canonical distribution E to the minus HWN. And what you're going to do is you're going to therefore generate sample from E to the minus HWN, and then you're going to push forward them to P, because by construction, P is the push forward of that extended distribution. In practice, you cannot integrate Hamilton's equation exactly. And so we've seen yesterday many ways to define integrators which preserve some structures. And when it comes to HMC, what you absolutely need is that your integrator is symmetric and time reversible, which usually it's just called reversible. That's associated to what's called the discrete time symmetry given by the momentum flip in the case of HMC. And you need them to preserve the phase volume, so they need to be volume preserving integrator. And the reason for that is because you're going to have a metropolis accept reject step, and under those conditions, that step is going to be quite simple because you don't have any Jacobian appearing. Okay. So the simplest case is just the manifold Rn, in which you have your target, you have your potential energy V of x related to your target density, and your kinetic energy is just the standard kinetic energy. In molecular dynamics, M would just be the diagonal with the mass of the molecules. In statistics, it's called the precondition matrix. In that case, the Hamiltonian field T and V can be integrated exactly. You have a solution for them, and therefore you can do HMC quite efficiently. But the problem is on a manifold, you're not going to have global coordinates. You're going to have a curvature, so you might leave the manifold if you don't integrate Hamilton's equation exactly. You're going to end up with non-separable Hamiltonian, so you're going to have a kinetic energy which depends both on position and momentum. And you're going to need basically to compute your geodesic flow exactly in some way. Right, so just mentioned briefly Riemann manifold HMC, which if you were here 2 years ago, Jeremy gave a talk about this in JSI in Paris. And in that case, you're in a Bayesian context. So you have a prior distribution over theta, the manifold, which is the parameter space, and you have some observation W. And you're going to define your Riemann metric. So your target density is determined with respect to the Lebesgue measure. And you're going to define your metric tensor, your kinetic energy, by essentially taking the Hessian of your posterior, averaging over the likelihood, and that's going to give you basically the Fisher information minus the Hessian of the log prior. And that is what you're going to use as your kinetic term. So that's why you have a log determinant of the determinant of G and PT G minus 1 of theta P. So in that case, the Hamiltonian is much more complicated, even though you're still on Rn. So you're going to have to use some more complicated integrator, which do not basically integrate exactly that, and there are some problems. I think in the original paper, they used the generalized leapfrog integrator, which works for non-separable Hamiltonian. But it's quite a complicated system, so in practice, people try to not use the Fisher information matrix for HMC. Also, you might notice that the Riemann manifold HMC has no manifold. You're on a Euclidean space. And similarly, there are many papers which give strange name to HMC algorithm, which are just basically HMC. So you're going to have papers called Lagrangian Monte Carlo, which just mean that you do HMC on velocity space, which was actually what you do originally. And you're going to have geodesic, say something called geodesic Lagrangian HMC, which just means you're going to integrate the geodesic flow, which is what you did originally. So basically, all these names are just HMC. And so the basic step of HMC are going to be that Hamiltonian system, that's step 2, which you integrate. But you're first going to do a momentum partial refreshment, because your Hamiltonian system kind of preserves quite well the energy, which means you're not going to have, your sample are always kind of going to be on the same energy level of phase space. So you need to refresh your momenta to change your energy level to have something ergodic. So you have a momentum refreshment, which, so originally it was a full momentum refreshment from a Gaussian, and then was extended to a partial momentum refreshment by Horowitz in 1991 to basically improve the acceptance rate at constant time step. The problem is that when you have a partial momentum refreshment, basically you end up, whenever you reject your sample in the last step with the metropolis accept reject, you're going to go backward. And so you're going to you're going to increase your correlation between samples. So it's not so clear that it's better in principle, although there are extensions of HMC which use what I'm going to go next, which are shadow Hamiltonian, which were presented basically in the last talk yesterday as modified energy. So there's an important property. Well, so as I said initially, your integrators for HMC just needs to be volume preserving. But in practice, you do want them to be symplectic, which is a stronger condition. And the reason why is that, as you saw in one of the talks yesterday, the modified equation of Hamiltonian mechanics, which means when you replace the continuous trajectory by discrete trajectory with a symplectic integrator, you can find a shadow Hamiltonian, so a modified Hamiltonian system, which passes exactly through that discrete trajectory. So your discrete trajectory is a Hamiltonian system for a different Hamiltonian, which is exactly preserved. And that's very nice, because that means that if you can preserve exactly your energy when you do HMC, it means your samples are always accepted. So you can use this thing called shadow Hamiltonian, which were proposed like 15 years ago for HMC. And they do improve a lot your acceptance rate. So when you combine them with a partial momentum refreshment, it does improve HMC quite a bit. There's one thing you should know about the theory of integrator for HMC, which is very different from the standard numerical integrator theory, is that you really, really don't care about reproducing well the Hamiltonian mechanics. So you're not trying to follow the true Hamiltonian trajectory. You're just trying to conserve energy. And so what you want to do as well is to reduce correlation between samples as much as possible, which means you're going to take very, very large time step, as large as possible. And usually in numerical integrator, what you're interested in is having integrators which are very good as the time step goes to 0. So you want to have integrators with a high order of accuracy. But that does not apply to HMC. So the recent work on choosing what is the best integrator is based essentially on applying it to the harmonic oscillator, which is the same as choosing your target density to be a Gaussian, and just trying to see how well your integrator performs here, so you tune it there, rather than looking at time step that goes to 0. But aside from that, the way you actually construct integrators is using the standard techniques that were introduced yesterday. So using, for example, discrete variational principle, the generators theory, and stuff like that. Okay, so we talked a lot about symmetries in this conference, and those are very important in HMC. And one of the reasons why HMC is quite useful is because, first of all, a standard property of Hamiltonian mechanics is that your Hamiltonian does not depend on a constant. And that's exactly why you can apply to unnormalized model. So which means models for which you don't know the normalization constant. Similarly, your kinetic energy is usually B invariant, so you can solve the geodesic flow. You have an exact expression for the geodesic flow. And basically some other properties of Hamiltonian system are what makes the numerical integrator have a very simple accept-reject step with no Jacobian appearing. So all this symmetry plays a very important role in HMC. Okay, so just last thing, the origin of HMC is from Gage Theory. So you have a Gage group. It originally was SU3. So you have a QCD. So QCD Gage Theory means you have a Gage group SU3 over spacetime. And what you're trying to calculate is you have your QCD Lagrangian, which is the Yang-Mills action, plus a matter Lagrangian, which has a Dirac operator and things like that. And you discretize that because you're going to work on lattice. So you have a lattice QCD theory. And what you end up is with your partition functional path integral, which is of this form, where U mu is called the link variable and discretize your gauge field, your connection one form. D is the Wilson operator, and you discretize your Dirac operator. And SWG is your Wilson gauge action, which discretizes your actual Yang-Mills action. And what you end up there is the important thing is that you have a du mu, which are SU3 variable. And so you end up having to integrate over SU3. So that's how HMC arises. You actually want to do that integral. Originally, you actually do not exactly want to do that integral. You want to do the U1 version of it. So it was a bit simpler. But a few years after, there was a generalization from Kennedy and Rossi to SU3, which explains how to do HMC on Lie group. So originally it was on U1, but then you want to construct the mechanics on Lie group, and you need to actually define a mechanics and a way to integrate the mechanics. But the problem is that you don't have global coordinates in general. But the nice thing is that you do have global one forms. So you have the Moore-Curtin frame, theta I, and you have a canonical action. So you have, we take it to be right action, so right action of the group in itself. And so what you can do, so that's a paper from Kennedy and Rossi, is that you can define a symplectic structure on the phase space, perfect. So that phase space, so the left trivialized phase space, where your momentum are just elements of the Colli algebra, and your theta I are the Moore-Curtin firm, and you can define your symplectic structure as just the exterior derivative of that. And what you get is the usual dx dp term, with just theta I that replaces dx. So when you're Rn, it's actually dx. And then you have an additional term which appears because the Lie group is no longer abelian. So originally they checked that this thing is actually it preserves all the things you need to preserve for HMC, but there was no relation to canonical mechanics. So for them, in Gage theory, it's really, you define that, it works, you're done. So you can define the corresponding Hamiltonian vector field and Poisson bracket, and you can define all basically your HMC scheme. So for SU Fourier, you choose your kinetic energy to be just your Cardan-Killing metric, and you can basically, that's your Hamiltonian kinetic and your Hamiltonian potential energy. You can solve those exactly. You take a representation, you can map your equation in a representation, and that's what you get. So essentially, you reduce the problem to have to compute the matrix exponential. So that is how QCD HMC arose, so the first HMC on Lie group scheme. So we're in 1989. So we're done, and that's all we're done when it comes to gauge theory. And the first question is how do we extend this to Lie group? And for some reason, people from gauge theory didn't know that, but what they wrote down is just a canonical symbolic structure. So I think people which are familiar from mechanics on Lie group know that that thing is just, the previous symbolic structure that I wrote is literally just writing the canonical symbolic structure, expanding it in terms of the momentum map, and just left trivialize. So rather than working on T star G, you work on G mod G star. And that means you can basically use the same thing for any Lie group, as long as you can compute your kinetic flow, geodesic flow exactly. And one of the nice things about HMC is that you choose your kinetic energy. So you can choose the simplest one to make your system to have an actual integrable kinetic energy. And so you can extend this way very easily to Lie group. In general, your kinetic flow is now given by the Erner-Aldol system. But for GLN, SLN, SON, SUN, you can basically choose your kinetic energy to solve this. And so essentially you're done with the Lie group part of HMC. And now the question is how do you extend that to manifold? And the easiest way to do that is just to consider at least the class of natural reductive homogeneous manifold. Because for that class of manifold, you can basically just continue to do Lie group mechanics as we saw, those equations of motion, and just do symplectic reduction. You're going to reduce your system, you're going to get a Hamiltonian system on the reduced space, which is going to perform HMC there. But the nice thing is because you're in a Lie group, you essentially have global coordinates, you have an exact geodesic flow, you don't have to do parallel transport because you left trivialized. You don't have to apply Lagrangian multiplier and all that. So that's one way we recently generalized. Well, there were HMC scheme on manifold from Simon Barn and Andrew Holbrook, but essentially, say the one from Simon Barn was just for embedded manifold in Rn, and there was no answer to how to compute the geodesic flow and the projection to the tangent space. But basically, the idea is just, so I'm almost done. You take any manifold of the form G mod K, any homogeneous space, and you're going to assume it's natural reductive, and therefore you have a natural reductive decomposition. Natural reductive homogeneous manifold include basically all the homogeneous manifold you can name. So Stiefel, Grassmann, and their complex version, space of positive definite matrices, which people talked a lot about yesterday, the complex version, Hermitian positive definite matrices. As a special case, you have hypersphere, complex projective spaces, blah, blah, blah. And so that's not such a strong assumption. You can slightly generalize it to geodetic orbit manifold, but I'm not sure that's useful for statistics. The reason why you want to assume it to be natural reductive rather than just homogeneous is because of the geodesic flow. So for natural reductive homogeneous spaces, you have a very nice complementary subspace P, where K is the algebra of big K, which is essentially all you're going to actually need. And you only need to compute the geodesic flow starting at a point as a velocity in P, which are of this form. So they still look like the B invariant geodesic flow, although your metric is not necessarily longer B invariant, because you're going to have non-compact Lie group. Say for SPD, you have GLN over ON. Yeah, so essentially that allows you to just reduce the problem of homogeneous HMC to Lie group HMC. And one of the nice things as well is that on Lie group HMC, because you have such a nice expansion of the symbolic structure, you can calculate your Poisson bracket and shadow Hamiltonian, which depend on the Poisson bracket very efficiently. There's been paper recently about how to do that. And so it's quite nice to just reduce the entire problem to Lie group. And yes, essentially what happens in practice that you start from your target potential on the manifold, you just lift it on the Lie group, which is very easy in practice. And then you're going to define the kinetic energy you prefer on your Lie group, which is going to be the one that makes the Lie group naturally reductive. So basically the map from G to G mod K is going to be a Riemannian submersion, which is a Riemannian isometry when you speak to the complementary subspace P. And as long as you start with your initial momentum in P, so your momentum refreshment is now just a vector in P, because of conserved momenta, you're going to stay there. And as a result of that, you're going to stay on the level set J minus 1 of 0, for those familiar with symmetry reduction, which means that when you reduce, you're just going to get canonical mechanics on M. So basically, you're just reproducing your original system, everything is preserved, and yeah. So basically, that's the final scheme for HMC on naturally reductive homogeneous space, and that's just one example. You can see a recognizable potential on the sphere, which you lift to S of 3. You do everything in there, and then you just compute the position. You just look at the position samples there, and you project them to the sphere, and you get what you expect to get. So yeah.